think of an oxidation reduction. There was one that went up on the board today in lab, and I said, we'll revisit this because it did not confirm what your hypothesis was. Okay. If I take zinc and copper and put them both into solution, one will oxidize the other one. One will reduce the other one. And the way that we know this is by looking in the appendix. I don't know, is it like Appendix G in our book? Did we look yet? I don't think we've looked yet in our book. I think we were up to Appendix G for something else, so this might be Appendix H. What we're looking for is a thing called standard reduction potential. I is formation constants. What comes before I? H. Wow, 2, 4, 6, 8 pages. 8 pages in the appendix of standard reduction potentials. Okay. Potential means we'll be looking at voltages. Okay. The individual number is a potential, and then we're going to look at the difference between these two. So, this is Appendix H. Hopefully they're alphabetical. There are 2 ways to write a standard reduction potential table. One is by magnitude. That's actually really useful, but you have to go seek what the numbers are. And then the other one is alphabetical. So I need the value for copper, and I need the value for zinc. Now, zinc is a ooh, I almost said something out loud. I was about to say zinc is a transition metal. But it's not.
Wait, it's changed, isn't it?
It's not. Let's go look on the periodic table. We would think that because zinc is a D block metal, it counts as being a transition metal. What is it? Who's taking inorganic?
Yes, definitely.
What is it that is special about the transition metals? They're variable oxidation states. See how that one's in a different color?
Yeah.
Zinc is 4s2 3d10. As a filled S shell that is losable, S electrons.
Yes.
You can lose those. And it has a filled D shell.
Yeah.
It is not breaking up those D electrons, and it is not going to lose 1 electron from the S. This is a fixed oxidation state.
Yeah.
It's going to go from zinc 4s2 3d10 to zinc 2 plus 4s0
Oh yeah.
3d10. Zinc has a fixed oxidation state. It is 2 plus. Copper, while I'm here, look at this. This is the beauty of inorganic chemistry. Copper is there. So its ground state, its ground configuration should be 4s2 3d9. That's a filled S and a part-filled D. Bad. Part-filled orbitals, bad. Empty orbitals, good. Filled orbitals, good. Half-filled orbitals, kind of okay. So that copper is going to steal an electron from the 4s and go 4s1, 3d10. So copper has two oxidation states that are possible, a +1 and a +2. So when I look at the reduction potentials in my appendix, I should be looking for the 2s, because the zincs only got the 2+. Copper does have a 1+. It's kind of hard to make it settle on 1+. If you want it to settle on 1, you have to control the atmosphere so that the atmosphere is non-oxidizing. You have to remove all the oxygen and all the moisture from your reaction. Otherwise, copper 1 easily oxidizes up to copper 2. So from the table, I want the values for zinc and copper that are the 2 electron reductions.
Copper has 0.339.
Okay, while we're here, this value needs 2 things. It needs a unit, which is volts, and it needs a direction. Yes. Does it say plus in the table?
No.
Okay, if it doesn't say negative, it's plus. Like energies, like enthalpies that are endothermic or exothermic, if it doesn't say plus, write it down. Okay.
And zinc 2+ has it negative 0.762.
7.
62.
Was that the number that you put up on the board earlier on today?
No.
No, it wasn't.
They didn't have plus and minus. Oh, we had to decide that, right? No, we didn't.
Yeah, so the number on the board went up wrong this morning. And I let it, because I knew I was going to talk to you about this. And it wasn't, it didn't matter at that time.
Okay.
All right, these have to be written as reductions. So am I turning copper into copper 2+, or am I turning copper 2+ into copper?
For the copper.
They'll both be the same. They're reductions.
Oh, yeah.
Is reduction the loss of electrons or gain of electrons?
Gain.
So here's my arrow. Means that the electrons are on the left-hand side or the right-hand side of the arrow. Here's my 2 electron reduction and 2 electron reduction. Oh. So I'm going to go from copper 2+ to copper 0. And from zinc 2+ to zinc 0. That's, oh, I'll tell you what. We've got a positive number and a negative number. Go through the 8 pages in the table and find me a value that's at 0. Just stick your finger down the column, find the 0. Find the reduction that has a potential of 0 volts.
Hydrogen.
Hydrogen does.
I'd love to see it.
Okay.
Just hydrogen.
Now is that plus 0 volts or negative 0 volts?
It does not have negatives, so it's positive, it's also 0.
Can you have a hydrogen atom? How is it written in the book?
2H plus
Okay. There's a couple of things here that we will discover along the way. We did this in chemistry too, but who remembers? Yeah. I can't have that be a hydrogen atom. That needs to be a hydrogen molecule because hydrogen atoms don't exist in nature yet.
Yes.
I mean, they're out in the galaxy somewhere, probably. But you know, we haven't found any down here yet. So there's two ways that we can do this. We can write that that is half of a molecule. Don't like that.
I don't like that.
I don't like that because you can't have half of a molecule. So our other option is that we take two of these and two of those makes one of those. Okay, now when that happens, do I double this number?
Doesn't matter. Well, I mean,
If it was a number, then yes.
If it was a number, then no.
No. Because it's a fixed
No.
number.
These are intensive properties. I didn't expect you to remember this from previous. They are intensive properties. Give me an example of an intensive property.
Specific heat capacity. We talked about this,
Okay.
and then you were like, you sent me an email about, we'll talk about it later, and then we never
Okay.
did, and then,
Well, she's
now.
trying to
That's
bring it back.
typical
up.
behavior. We'll talk about it after spring break. See what I did there? Boiling point. Water boils at 100 degrees. What if I doubled my amount of water? Then surely it would boil at 200 degrees. No, it doesn't. That's an intensive property. It's completely independent of the amount that you use. So there's going to be a temptation later on when we take something and we realize, oh, I'm going to need twice as many anions for this thing. And when I double it, I'm going to be tempted to double these numbers. These numbers don't change.
Yeah.
They come out of the book and they're used the way that they come out of the book. Okay. An intensive property is independent of amount, which means don't multiply them. All right. This is our zero. We set hydrogen behavior to be zero. And numbers that are on the positive side of hydrogen do something, and numbers that are on the negative side of hydrogen do something else. There's actually something called a standard hydrogen electrode. We've got lots of electrodes in the cabinet. We should have a look. Have an explore. That number is big, bigger, and this number is smaller. These values are called standard reduction potentials. E is the potential. Standard puts you a little superscripted zero there. What does standard mean? So everything that could make that number change value has been accounted for. So that means that when this number was found and put in a textbook in an appendix, it was done at the same temperature and the same pressure and the same concentration. Standard conditions is 1 molar solutions. One atmosphere of pressure, that's not really going to make a difference to us, and 298 Kelvin. When we did the gas laws, the standard temperatures pressures for the gases was 0 degrees Celsius, which is 273. But guess what happens when you make your solutions be at 273? They freeze. So we set it to room temperature instead. It's high time that the gases were at room temperature too. Okay, so these two values were found at the same conditions. They are standard and they are reduction potentials. Just for giggles, turn that one into an oxidation and put a number to it.
Positive 0.762 volts.
So to turn this reduction, gain of electrons, into an oxidation, you would turn it around, and the oxidation number increases, you lose electrons, and the value gets to be plus 0.762 volts. You really should write the pluses and the minuses in.
So you look at it?
Yeah.
Because you flip the reaction.
Okay.
Oxidation is the reverse of reduction. Now, the same way that we could have had an appendix that was all the Kas, and then a follow-on appendix which was all the Kbs, but we decided we're only going to have one table, and that table is only going to be Kas. And if you wanted to know about a base, you had to think about what its conjugate acid was, and then go find the Ka for the conjugate acid, and then turn it into a Kb. We could have an appendix that has all the reduction potentials in it, and then another appendix that has all the oxidation potentials in it. But knowing that they are just the opposite of each other, I'm only going to give you one table. Reduction potentials. That probably comes around because at the birth of this science, which is now 200 years old, this is Michael Faraday. So we're talking about the 1820s.
1820?
Yes, 200 years old.
Yeesh.
Faraday took solutions and turned them into metal, extracted the metal from it. He was the first person, said this morning, to isolate sodium, and then they isolated like lithium and a handful of other metals that we knew existed, but nobody had ever seen them. But we could just generate them, because now they're linked to a voltage, and Faraday basically invents a method for generating electricity. So now we can make metals that were not possible to make before. We could reduce them. Okay, I have a big number and a little number. What does that mean? Big positive number and a negative number. The positive number means goes, so it's big and positive, goes in the direction shown. And the direction shown is that way. This number's negative. And that means that this reaction wants to go in the opposite direction. It wants to go this way. Okay. I put copper and zinc together in solution. Who wants to be reduced? The copper or the zinc?
The copper wants to be reduced.
That value is more positive than this value. Means this one wants to be reduced, wants to go in this direction. Metal plus electrons means a decrease in your oxidation number from +2 to 0. So that means that when zinc and copper interact with each other, the copper gets reduced. What is the copper 2+ doing to the zinc?
Oxidized.
It's oxidizing it. So the thing that gets reduced is an oxidizing agent. The thing that gets oxidized, so the zinc wants to go the other way. It wants to turn from zinc metal into zinc 2+, into the zinc ion. So you put copper, if you took a solution of copper and zinc, they would fight it out and the copper would reduce the zinc. Okay.
The copper would.
Did I say that? Right? No, the copper gets reduced, the copper oxidizes the zinc. Zinc has a big negative reduction potential, which means not only is it not going to get reduced, it really wants to go the other way. We coat things with zinc to stop them from rusting.
Pennies.
Pennies don't count.
They don't count.
No, but they use zinc. Zinc's not cheap anymore, but they use zinc because it's cheaper than other metals.
Okay.
Anybody drive an expensive German car? So, American cars, Italian cars, Japanese cars to an extent, they rust. But your expensive cars from Germany, they don't rust so much because they're steel iron. Steel is iron, just treated. Steel wants to rust, iron wants to rust. But zinc wants to be oxidized much more than iron does. What's the reduction potential for iron? There'll be two in there. There'll be one for iron 2 and one for iron 3. In fact, there might be one for iron 2, 2 iron 3.
There's one for 3 to 2 for iron, and that is 0.712.
Okay, so we want the one that goes from the metal itself. So there should be one from iron 2 to iron 0.
Yeah, that one is negative 0.44.
So iron's reduction potential is here, close to 0. Zinc's reduction potential is here, much, much more negative. So if I've got a piece of iron that I want to prevent from rusting, I put a very thin layer of zinc on it. And when the seawater, or whatever it is, comes, salt water, comes to try and rust my iron, the zinc just says, no, oxidize me instead. I would much rather be oxidized as a zinc than iron wants to be oxidized. And we call that galvanization.
Oh, I remember hearing about that.
And if you've got an expensive German car that's made out of iron, steel, before they put the paint on, they dip it in a tank of zinc and flip the switch and plate a thin layer of zinc over all the steel. And now when it gets a paint chip, the salt water doesn't get in and rust the iron. It oxidizes the zinc instead.
What other cars do? They're only the expensive ones do that?
Yeah, it's expensive. It's an added expense. And if you know anything about the auto industry, everything has been chiseled down to the last penny. Okay, so when zinc and copper come to fight it out, they're gonna go this way. All right, let's go figure out if I made a battery out of this, how much voltage could I generate? So we're gonna build a battery. He says, knowing full well that's a lie. What's this? It's not a battery. That is a cell.
Yes.
What's this?
That's better.
This is a battery.
Oh.
Battery is a combination of cells. But language is fluid. It gets to not stand up. There was a big argument on Reddit yesterday over somebody said, look at this 4-story building. And they had said that the building was 4 stories high. It's 4 stories tall. And half the internet went, you've done that wrong. Because it's not a story. It's a story. It's a different word.
Wait, what?
It is?
Yes.
Story?
Yeah. Floors in a building are called stories.
What?
The thing that you read to your child before they go to sleep at night is a story.
Forget it.
They're completely different words.
That's terrible.
And there was a huge backlash of, we don't care about that anymore. This is the word that we've decided, America, to
Wow, everything.
yeah. So cell batteries and batteries and cells.
Me neither.
You can't control language. Once the humans interact with it, you cannot control it.
Well, it's like riz. What the heck? I don't like. I hate the word riz. Whoever came up with the word riz.
It won't be here
Stupid.
next year. It'll be gone.
It was the word of the year last year.
No.
And
Yes.
it's in a dictionary now.
Yes.
So is nincompoop. It's things that people don't say anymore. Poppycock's a really good word.
What is it?
Poppycock.
Like
Poppycock
this
is a very polite way of saying in English, oh, that's nonsense.
That's a nice way of saying it, poppycock?
That sounds so much weird.
It sounds so mean.
So how would you use it in a sentence? Oh, that's poppycock.
Next time we get an answer
you
wrong.
just say something that is, you say something that is obviously wrong. Like,
2 plus 2
Taylor
is 5.
Swift is the best rock guitarist of all time.
No, I got one.
Poppycock.
Boy.
Oh boy, that's poppycock. Booey!
Boy, that's my bar.
Yeah. Anyway, poppycock from the original Dutch poppycock, which means soft excrement. Lovely.
But it still sounds like so many poppycock.
Mm.
That's why it's not a nice word.
I know.
That's not a nice word.
So we are going to do this reaction, but we're going to separate the components of the reaction from each other. So that they're not all in the same container, like you did this morning. So we would take a beaker or container and then another one and put them side by side, and into one of them I would put the zinc 2+ salts. How am I going to guarantee that the zinc goes into solution? All nitrates are soluble. So my best candidate here would be zinc nitrate. And then in the other one, I put the copper. And my best candidate here, because all nitrates are soluble, would be copper nitrate. And then I put a piece of metal that is zinc metal. When something's in its zero oxidation state, that's how it occurs in nature. And then into the other, I put a piece of copper metal. And then I attach those together with a conductive wire and feed them into a voltmeter or a light bulb or a remote control for the projector. Okay. And I wait for the electrons to flow from one place to the other.
But you won't find out.
They will for a bit, and then they will stall because there's nothing to equilibrate them. That's where your piece of porous paper. In reality, what we would do is we'd have a little sinter. A sinter is porous ceramic, and so it would be part of the glass. These two would be attached together, and then there would be a ceramic here that holds things in, and we put the electrolyte in there. I'm going to write that as, well, we use potassium nitrate, right? There you go. But as long as this is soaked, it will help. Okay. Which direction do the electrons flow?
From the zinc to the copper.
Oh, in the red, what's happening there?
That's an oxidation.
This is an oxidation. And oxidation is loss of electrons. So the zinc metal loses its electrons. And those electrons flow this way. What's the flow of electrons called? Current. So, yes, I have a potential difference, but I also have an I have a current flowing, okay? And then that means that positive charges have to flow back in the other direction. And if we don't have the salt bridge, then I might get a surge of electrons as these things say, oh, you want to be reduced, I want to be oxidized, let's exchange electrons, but then there's nothing to equilibrate it, okay? I have two electrodes. Electrode 1 and electrode 2. I feel like this ink is not going to come off the board. Oxidation happens at this electrode. These two electrodes are not the same as each other. They need different names. I'm going to call this one the anode. And reduction occurs at the opposite of an anode. Called a cathode.
Does it matter which one you make the anode?
Yes. Yes. Yes.
So it has to be at the oxidation.
Yes. Because the amount of electricity, the amount of potential difference, voltage, that this generates is equal to the reduction potential of one of those numbers, subtract the other one. And you have to know which order. Okay? Now the way that we've decided to do this is slightly different than the way I was taught when I was a student. The way that I was taught when I was a student was reduction plus oxidation. But there's a problem there, because all of the numbers in the book are all reductions all of the time. And in order to turn a reduction into an oxidation, you have to flip it backwards and invert the number. So now they say reduction minus oxidation. But, yes, but it's reduction minus oxidation,
Well, yeah.
but it's the reduction potential of the reduction minus the reduction potential of the oxidation. Okay, and after you've written it out a couple of times, you say, I can live with this. It is the reduction potential of the cathode cathode is the reduction. It's where the reduction happens. And then we're going to subtract from that the reduction potential of the anode, where the oxidation happens. And you can remember this because of red cat. Reduction happens at the cathode. reduction happens at the cathode. Okay? This way we get to use the numbers that come directly out of the book, and we just subtract one number from the other. The previous way was this number plus the oxidation potential, which is this number reversed. And the reverse of a minus is a positive.
Yeah.
Okay? So slightly different than the old way. All right. If this is performed on 1 molar solutions at room temperature, those numbers come straight out of the book. And my standard reduction potentials turn into a standard cell potential. Okay. How many volts will this thing generate? Copper and zinc.
Copper, zinc.
Copper is positive 0.339 minus negative 0.762, which is copper.
339.
7 what?
And then negative 7.762. I got a self potential of 1.101. 101 volts.
I'm only allowed 3 significant figures. There you go.
Did the number change? From copper to 0.339.
Is that the number that was on the board a minute ago?
That's what I'm down.
What did you write down?
I'm using the one from last year.
Okay.
Mine is a 0.34, 0.34. I got the same number.
Yeah, so that's just a 2. That number is just a 2
Oh,
digits.
it's just rounded.
Yeah, this is to 3 digits of precision. It's the same number. Same number. Okay. We just generated a cell voltage, and if I string a whole bunch of these together, I make a battery, and I can drive a light bulb, or a propeller, or something else. Okay.
So you said there would have to be multiple of these for it to be considered a battery.
Yes,
This is not a battery.
that's a cell. I think we did this in chemistry too.
Oh yeah, I think I have a photo of this. It was different
Cannonball.
different.
That's a cannon. That's a battery. So battery is the name of a whole rank of cannons. It's a military name, named after battering things, because that's what you do with cannonballs. So this is a battery of cannons. And when people made these, they went, we'll call that a battery.
How would they do that?
Because it looks like a bunch of cannons all piled up together.
Really?
It could be
Okay.
original.
What does Wi-Fi mean?
Wireless something or other.
What's the phi in Wi-Fi for?
It's like
You never
wireless
asked yourself?
frequency. Is it like
No.
wireless? I have, but I forgot what it was. Was it like wireless frequency or something?
No.
No.
No, it's a joke.
There's Wi-Fi.
It's a joke.
It's a joke.
Yeah. So it doesn't mean anything. It doesn't mean anything. It's a joke. It's a play on words. It's a play on the words from hi-fi. What does hi-fi mean?
Huh?
Yes. The hi-fi, your record player and your cassette deck with the big speakers that you have in your house with the shag pile carpet.
Okay.
High fidelity. So hi-fi equipment is the amplified equipment that you play music through. And when they invented wireless networks, somebody thought, oh, we'll just call that Wi-Fi, because Wi-Fi rhymes with hi-fi. And
Yeah, I feel
Wireless
yeah,
fidelity.
it's stuck. It means absolutely nothing. It doesn't mean anything at all. These are language cannot be controlled. These are words that have no literal meaning.
That's terrible.
Who's your favorite DJ?
DJ.
You don't have a favorite DJ?
No.
No, it used to be Tiesto. Tiesto used to be popular. Or whoever.
Wait, when you say DJ, what do you mean? Like they literally coordinate the music, or you talking about
DJ Khaled.
Who?
DJ Khaled.
What does DJ mean? Why is everybody a DJ? You know, there's all these world famous DJs now. They make hundreds of millions of dollars. Like Steve Aoki's worth millions and millions of dollars, and all he does is play records and throw cakes at people.
Oh, he doesn't throw cakes?
You've never seen Steve Aoki throw a cake?
No. Dr. McGuire, I'm so sorry.
You're killing me.
You're killing
YouTube. Steve Aoki. Cake throw. A-O-K-I. I can't believe that you guys don't know this. Steve Aoki is. Of course he does. So when you go to a Steve Aoki concert, he plays music, dance music.
Oh yeah.
And then he throws a cake at people. And sometimes spectacularly. He's got a really good aim.
He's worth over 150 million.
What?
Yeah. Okay.
He just throws at the crowd. Like,
And they're happy about this?
Oh yeah.
To get
People
cake?
want to be caked.
To be cake?
Yeah.
I would be so
what?
He's a DJ. Why is he a DJ?
I don't know.
What does DJ mean? Disc jockey.
Desk jockey.
Now, why is he a disc jockey?
Well,
Not
any-
The disc on the.
So the disc is from the old vinyl records, where there's 7 inches or 12 inches, but he's a jockey. Doesn't make any difference. It's a joke from a military word, which was desk jockey, that when you got injured or demoted in the military and you couldn't go and fight the remainder of the war, you rode out the remainder of the battle sitting behind a desk. And jokingly, they became desk jockeys. Desk jockeys became disc jockeys, which became DJs. It's just a word. It means absolutely nothing. So, battery doesn't mean anything. Okay?
My world is.
This. We're going to write this way. This is a zinc. It's a metal. You can put the 0 there. And then it's separated because it's solids and solutions from the zinc solution. And then there's a salt bridge. And then there's the copper solution. And then there's the copper metal. That's how we write the cell. Okay. Let's throw some numbers at this.
Let's throw.
I can't believe you guys are so completely uninformed about pop culture.
Oh, I stay out of pop culture intentionally. My culture's from 60s, 70s, and 80s.
They had DJs in the 70s.
They did, but that's not the music.
Emperor Roscoe.
I just listen to independent artists. I've never considered DJs. Wait, so Run DMC, they had a DJ. Like they were the singers.
Jam Master Jay.
Okay.
They just finally arrested his murderers last week.
Is who murdered?
The people who murdered him.
He was murdered? I didn't even know that.
He was murdered over 20 years ago. And everyone knew who did it, but there's been documentaries about who did it, but they never brought anybody to justice until last week. They arrested his cousin.
His
Did they find DNA and stuff? Or
No, I think finally somebody came forward and gave testimony.
20 years?
Yep. I saw Run DMC once. They were good. All right, applications. We're going to make batteries, we're going to measure voltages, but we can answer questions. We can answer yes, no questions too. Like, can iron, ooh, iron. Have we done that one? Yeah. Probably the same notes. Silver. In silver chloride. Okay. So, we would take some iron and we would take some silver chloride. Are we going to put that in solution? Yeah. And then I've got that being in solution. You know that silver chloride really is not likely to be in solution very much. And all right, so this is going to go from iron 0 to iron 2+, whereas the silver 1 goes to silver 0, so you need twice as many of them. And it balances like that. We can ask the question in reverse. Okay, go find the E cell. So we had the value of iron a minute ago, but we didn't have it for silver. Okay. So I need to know the reduction potentials for Ag plus an electron goes to Ag0. That value is plus 0.80 volts. And the reduction potential for iron, what are we doing? 2 plus 2 electrons goes to iron 0. That value is negative 0.44 volts. Which sounds slightly different than the number that you said out there a minute ago. But that's the number that we're working with. All right, first up. We go from silver plus to silver 0, but there's 2 of them. What do we do to this number?
Nothing.
Nothing at all. The reduction potential for 1 silver plus going to silver 0 is the same it's an intensive property. Okay. Who are we asking to reduce and oxidize? So the iron, that's an oxidation. I'll just say iron. And this one is reduced. Okay, so E cell is the reduction potential of the thing being reduced minus the reduction potential of the thing being oxidized. Okay? Which is plus 0.8 volts minus 0.44 volts. Okay. All right, what does the positive value mean?
The cell can do.
Goes in the direction shown.
So the iron can replace the silver ends.
So my answer is yes. And there's a thing that they teach in like high school AP, it's called a spectrochemical series. There's a big long list of can this replace that? And it's this. It's this. They make students memorize that stuff when you shouldn't be memorizing anything in a table. You should just figure it out. All right, so I've been tipped off that we've already seen this problem before. So you're probably going to see you've probably seen the next set of questions, but I can change them. Is your next set nickel and iron?
No.
He's lying now. What's the next thing?
Yeah, it is.
It is. All right. Then let's go do something bigger. All right. There's a couple of things in here that we'll get to. And we'll do it. We'll do it last. We'll do the delta G thing last. All right. A lot of this kind of chapter gets devoted to batteries exist. Let's mix two metals together and see what kind of voltage we can make. But there's bigger stuff out there of there are real redox reactions where I have something I want to achieve and I throw an oxidizing agent or a reducing agent at the thing that I want to react with. Okay? So let's talk about agents. An oxidizing agent is something that causes its surroundings to be oxidized. Okay?
So are we talking about an external, something that's not already in the equation? How you're saying something?
You're gonna put it into the equation.
going to be a reagent that causes whatever it touches to become oxidized. Now, when you're oxidized, what happens to your oxidation state?
Wait, repeat that question.
When you are oxidized, what happens to your oxidation state? It goes up. So when you are oxidized, we can recognize that as an increase in oxidation state or oxidation number. And sometimes that's from a positive value to a bigger positive value. And sometimes it's from a negative value to a less negative value. Sometimes it's from a negative to a positive, sometimes from negative to 0. The reagent itself, if it's making its surroundings increase in oxidation number, then itself must
Decrease.
So the reagent itself gets reduced, which means a lowering of oxidation state. Okay. So if you were a good oxidizing agent, would you have a low or a high oxidation state when you start? High.
So it's reducing. So in order to reduce a lot, if you oxidize others a lot, you have to start up high so you go.
KMNO4 is called potassium permanganate. Okay. What's the oxidation state on the manganese? All right, let's figure it out. What's the oxidation state on the potassium? Potassium has a fixed oxidation state. It's in group 1. What's the oxidation state on the oxygens?
2 minus.
It's in group 6. There's a fixed oxidation state. 2 minus. And there are 4 of them. What's the oxidation state on the manganese? That's the highest that we can get. Permanganate is only capable of reacting by becoming reduced. It cannot itself get oxidized anymore. It's at its limit. +7 is as oxidized as you can get. Therefore, when KMNO4 reacts with anything, it itself must lower this number. And there are 2 textbook examples of how that happens. One is in acid and one is in base. In base, that KMNO4 goes down to manganese 4. Currently, it is manganese 7. In acid, it goes down to manganese 2. It's a 5 electron reduction, oxidation. It's being reduced, it oxidizes its surroundings. 5 electrons for every manganese. That's really powerful.
Does that make potassium permanganate dangerous?
Would you like me to set it on fire and be incapable of making that fire go out?
Wait,
Yes,
is
we
that
can
the
do
one
that.
they use underwater?
Yeah.
Whenever they're.
The underwater flares are purple. That's the manganese. How can the fire be going on underwater? It has its own source of oxygen. Fire needs three things: fuel, a source of ignition, and oxygen. And if your material has oxygen already built in, you can't put it out. This is potassium dichromate. And its simpler form is potassium chromate. What's the oxidation state on the chromium? This is chromium 6+ in both of them. Okay, let's look at some dichromate. I think we're going to do dichromate oxidation. Okay. Oh, this pen's going. If we perform this reaction in acid, it's the difference between doing it in acid and doing it in base. If we perform this reaction in sulfuric acid solution, potassium dichromate will oxidize potassium iodide to iodine. Okay. Now, when you write the balanced equation out, and then you follow it with the total ionic equation, you can start crossing out the spectator ions. K2 Cr2O7 plus some amount of sulfuric acid. That's going to become a problem. We're going to really have to think about how to balance that. Plus potassium iodide goes ahead and makes, I think we're going to go down to chromium 3. Oh, I can't use those iodides. Plus iodine. And what else have I got? And water. Okay. So this isn't going to work particularly well, because we're going to go chromium 3+. All right. So that's 6+. I need that. Huh, exactly.
Where's the
But how did, but where, oh,
where did the potassium go?
The potassium. Well, there's a good chance that the potassium is is making potassium hydrogen sulfate. It's not in my picture. It's not in my diagram. So, let's go ahead and save this. Remember that this is what, it's not even in the book. So the book doesn't even attempt to do this. It just goes straight to the net ionic equation. Sulfuric acid is dibasic acid, diprotic acid. It has two H pluses to lose. The first one is a strong acid. And then the second one is HSO4 minus, which would be potassium hydrogen sulfate, which is in equilibrium. So that general chemistry text that says you're losing both of these H2s is probably not true. It's probably not true. And the potassiums take that up. Okay, so that's not balanced. Not balanced in any way. Do you want to try and balance it? No. Let's not. We're going to have the potassium, so the potassiums, right, they're strong electrolytes, they're just going to float. The ionic equation here, dichroming, every one of those, which is an aqueous solution, reacts with 14. Yeah, there is we could have done the permanganate one. When you go look in Appendix H, you'll see that it's written in the appendix. Where are we? The manganate and the dichromate are cousins to one another. They're very close. I can't find it. Come on. Come back. Standard reduction potentials. So we would go M for manganese. And we would find that MnO4 reacts with 4 H pluses and 3 electrons to make manganese 4, that's the one that's in base, or 8 H pluses and 5 electrons making the manganese 2. So it's all in the book. It's all in the book. And I remember looking at this as an undergraduate going, how am I ever going to remember that? Because it's not just iron 0 to iron 2 plus and there's 2 electrons there. Now there's other things involved, but this is the real world. Okay. Plus six iodides. Go ahead and make out 2 chromiums. So they both have to be accounted for, and we get the reduction down to chromium 3 plus. And then when I figure out if I have 6 iodides that have to match the number of electrons, that means I have 3 iodines. Iodines are solid. And if I have 14 protons and 7 oxygens, then I need 7 waters. This is not the most obvious thing in the world to balance, but it can be done. Okay, now, what's being oxidized? Okay.
The iodines.
It's not obvious. What's being reduced? That's my reduction. How many electrons are involved? That's a 3 electron reduction from 6 to 3. But there's 2 of them. This is 2 3 electron reductions. Okay. And what did we decide was being oxidized? So an oxidation is the oxidation number goes up. Iodine's in its naturally occurring form as a 0. But -1 is lower, less positive than 0. How many electrons are involved in this oxidation? And there's 6 of them. Break those into half reactions. We're done for today. Break those into half reactions. When we come back, we will build the cell. No. Break those into half reactions. Build the cell. The reduction potential for the iodide to iodine, reduction potential plus an electron is 0.54 volts positive. And the reduction potential for the chromate, dichromate, is equal to plus 1.33. Spring break.
Yeah.
Build me the cell, tell me the cell potential. Have a good spring break. See you in a week and a bit's time.